by Schutz, where he talks about these things in great detail. Okay, so let's move on to the last topic from this diversion that I have prepared. So it seems like this whole class is being taken up by this diversion. But this is something, this is not going to be very rigorous, but I think it's worth mentioning because those of you who are interested in getting a bit of geometric intuition, you might enjoy it. And the idea is that how to think of integration and the Jacobian, okay? Just 1 second. I think my cat wants to go out, so I'm just gonna let him out. Go, Chaka. Go, 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 go. All right. Sorry, these are not the kind of issues we usually face in class, but it makes life more interesting to have a cat in the classroom. All right, so integration and Jacobian. So this will be quite qualitative, but suppose that, when we do one-dimensional integrals, a lot of times, we have stuff like this, f of x, d of x, but then we make some change of variable, right? Say x goes to u of x, right? Then d of, then what we do is that we say, okay, in one dimension, it's very easy. We say, okay, d of x is going to be d of x by d of u times d of u. And then this function becomes, f prime of u, d of x, d of u, d of u. Let me just use a different notation here, g, right? Because if you express f in terms of it's as a function of u, it won't have the same functional dependence, right? So, this in integration, this is what we call the Jacobian factor. So, but, when we go to higher dimensional integration, we get up the determinant of a matrix there, like a particular matrix. And it's kind of weird, like, how does that come about? So here I'm going to give you an intuitive, idea about that, and that's related to the idea of orientation. So when we are doing a one-dimensional integral, you can think of it as a kind of a line integral, right? And then we know that whenever we change the sense of the integration, if we change the direction of the integration, we pick up a minus sign. So you can call that a change in the orientation. So all integrals have some sort of orientation. So for example, if I'm doing a surface integral, so I'm now going to do a two-dimensional integral because that's what's interesting. We actually have to, suppose you are doing this integral where you're doing f dot a over some surface S. And here's that surface. You have to choose the direction of the area vector to be either in that direction or in the opposite direction, right? Do you agree? Because that will change the value of this integration by a minus sign. Because the dot product, right? So, so what we do is that we can encode this orientation of this surface integral by saying that if I integrate in one orientation, so the integral variable, the differential element dx dy, I introduce a product which is called a wedge product, and the wedge product has the property that if you exchange the differential, then they pick up a minus sign. Okay. So what I'm saying is, this guy, this direction. So what does this mean? This means dx dy in this direction. And what does this mean? So without the minus sign is outside. That means that it's this it's the integration of a d of dy, but in the opposite direction. Okay, and they're of course related by a minus sign. So this is just the definition of this product. This product is called a wedge product, and as you can see, it's an antisymmetric product. So when we are doing an integration, a surface integration over or with some function in like this, we are taking this orientation, okay? Now suppose we make a change of coordinates. So we say, okay, let's introduce some new coordinates, u, which is a function of x and y, another coordinate v, which is a different function of x and y. Because we're in 2 dimensions, we're going to have 2 coordinates. So, this f of x and y will change to something g of u and v, which of course will depend on which function is this. But what happens to this guy? Something magical happens because of the antisymmetry. If you have dx wedge dy, this kind of product, if I took a dx wedge dx, what would this be? If I have an antisymmetric product with something with itself?
0.
Right? Because it's antisymmetric and we are taking the product with itself. So this thing, we can now express dx as partial derivative of x with respect to u du plus partial derivative of x with respect to v of dv. Right? This is just this part wedged with d of y du d of y dv. Of course, I'm not writing all those like, something has to be constant, all that. So now we get 4 terms, but here you see that 2 of these terms will be du wedged with du. But of course, we see that if you wedge something with itself, it's going to give it 0. And then we have another term dv wedged with dv, and that is going to give me 0. So only the cross terms will survive. And what will be the cross terms? It'll be del x, del u, del y, del v minus del x, del v, del y, del u times del u wedge del v. So this is exactly what we called the Jacobian, or the inverse of the Jacobian, I forget. Right? So when we do a change of variable, we are told in calculus class, and you memorize this, that, oh, you change this by, replace it by this function, you change it by, say, du dv, but then you have to multiply it by some funny Jacobian. But here we see that this just comes about very naturally from considering the fact that integrations have orientations. Okay, so there's something very beautiful and geometric going on here. Of course, this Jacobian, what it means is that geometrically, by an example, so if you are in Cartesian coordinates, so this is our x and y axis, when we say dx dy, what we mean is this little grid. So you go dx this direction, dy this direction. But of course, if we go to spherical polar coordinates, then of course, then the curvilinear lines they go out from the origin like this, right? So I'm trying to put in some perspective as well. And then, our little grid is no longer a square, but something like this. And of course, this thing, this thing is not d theta. It's rho times d theta. And this thing is d rho. And this is really comes from the Jacobian factor, right? So, when you guys learned curvilinear coordinates, you were told about these things, the geometric interpretation. But we see that over here, if we do this, if we took into consideration the orientation and the antisymmetry of the area measure, then we get that for free. Okay, so this is just something as an aside. You don't have to really understand this if you don't want to. You can just switch off. But if you want to, you can look into it more deeply and learn about differential forms and stuff like that. But that's not necessary at all for this class. Okay, so let me stop there in terms of the calculus diversion and take some questions. Okay. Any questions?
I don't have a question, but I just wanted to say, since I was the one who suggested to do the partial derivatives, that I really like the part on the identities, because I was under the impression that maybe there were some identities that I was missing, which is why I couldn't do the problems. But I suppose these are all you need in order to do partial derivatives.
Yeah, I think at this level, yeah, that's about it. I mean, the thing about identities is that you can introduce as many identities as you want. Identities are like, the germ of an idea has so many identities, hidden in it, right? So my suggestion is that, yes, just like, see if you know all the basics, and at some point you might need an identity that you don't know, but don't worry about it. Just if you come across something like this, then you just say, okay, I will just make it a new, you'll just learn it. Okay. So if somebody has asked a question, any book that you suggest on differential forms? So on the top of my head, there's a old book by Flanders, I think. Flanders differential forms, but there's something more modern actually that came out when we were students at Cambridge. Differential forms. I mean, I've actually never read a book on differential forms. I'm usually like, I just read the basics and then differential forms and connect. No, I think it was called differential forms and physics. Forms and physics, because you probably want. Okay, let me post it later on. Okay, let me just not interrupt the class for that. Okay, any more questions?